Good morning, everybody. This is Drew Bartlett. I am the Executive Director for the South Florida Water Management District, and I want to welcome you to our first Water and Climate Resilience Metrics Workshop hosted by our own Dr. Carolina Moran. As you know, we have made a lot of investments and we're strongly committed to thinking about and understanding the impacts of sea level rise and climate change. And that started when we hired Dr. Moran about a year ago. And since then, she's been leading an effort to draft new water and climate resilience metrics that we're going to present to you today. This workshop will summarize the recommendations of our internal and I might say talented group of scientists using our data to really understand what we're seeing over time with respect to climate change and resiliency. Hopefully these metrics will also help inform, the stakeholders, our partner agencies, and local governments on all of our resilience strategies as we collaborate and plan for the future. We really, truly appreciate this opportunity to engage you, engage so many people through Zoom technology regarding this information and science. And it's quite a packed agenda. And if you're into science, you're going to really enjoy it. We really look forward to whatever feedback we get and further engagement with respect to these metrics. I've been briefed and I find them fascinating personally. So thank you everyone for participating in this workshop. And I would like to proudly turn it over to our District Resiliency Officer, Dr. Carolina Moran, to take you through this workshop. Dr. Moran, it's all yours. Thank you for joining.
Thank you. Thank you very much, Executive Director Drew, for this introduction. Good morning, everyone. Thank you for your interest to join our discussions today on water and climate resilience metrics. So far, one of our major resilience initiatives that we are advancing at the district. And thank you also for the demonstrations of support that we already received from some of the stakeholders registered for this event. We feel that we are kicking off an important initiative and we count with your continuous engagement from everyone that is participating here today and other interested parties. Thank you again. And before we start, I would like to introduce our moderator, Mrs. Yvette Bonilla, who will go over some housekeeping items with you.
Thank you, Dr. Moran. And thank you everyone for participating. Throughout today's workshop, you will see a Q&A feature in your Zoom. If you would like to ask a question during the presentation, please type in your question and one of our panelists will do their best to answer your question by writing it back in the Q&A. When the presentation concludes, I will read a question that were not yet answered. At the end of the Q&A session, we will open the floor for the public comments. If you have any additional questions after the workshop concludes, please submit your questions using the Ask Us button on the top of the South Florida Water Management District's homepage at sfwmd.gov, and we will get back to you as soon as possible. Members of the public who wish to comment may use the raise hand feature on the Zoom. If members of the public are having trouble and need help, please go to our website at sfwmd.gov and click the Ask Us button on the top of the page, and we will assist you. If you are using a phone and would like to comment, please press *6 to mute and unmute, and *9 to raise your hand. Public comments will be taken, and during the public comment section of today's workshop. This meeting will end at 12:30 p.m. With that, we are ready to begin, Dr. Moran.
Thank you.
You're welcome.
Thank you very much, Yvette. And we also have one vision Please note that the water quality presentation by Dr. Nana Irikan will be focusing only on specific conductants and not include dissolved oxygen at this time. We'll be happy to share information on dissolved oxygen with you later upon request. So let's start the presentation of our major initial findings on water and climate resilience metrics. I'd like to share that the presenters here today are representing a group of about 30 technical staff who have been working for the development of these initial results in the past 6 months. It has been an honor to serve as the overall coordinator for this effort, and also having the opportunity to interact with such an incredible group of experts. In addition, this work is only possible because of the vast monitoring network that is managed by the district, and also the long tradition in providing full access to its robust data sets through our famous portal, the DB Hydro. I'm trying to move the slides. I'm just making sure I have control. Yes, good. So I will start by reminding you about a very active year. 2020 brought us many unique challenges, and among them a very active tropical storm season that extended from May 16 to November 18. We are very grateful that Florida did not experience a major direct heat from any of the record-breaking 30-name storms. But still, we saw many significant impacts in different parts of the state, including Hurricane Isaias, Hurricane Sally. And later in the year, while billions of dollars damages were still being identified throughout the United States, we were hit by Tropical Storm Eta. The major impact caused by Tropical Storm Eta was a significant amount of rainfall, especially in some western Broward areas that receive extreme rainfall between 50 and 100 return frequency. As illustrated in this map on the left, the red and the orange areas are the ones that receive those more significant rainfall events. The chart on the right shows a summary of the operation at C11 Canal East, where we can observe higher tailwater elevations before the start of the event. So focusing on this left portion of the chart here, before the start of the rain, the gray line here illustrates the observations, the tailwater elevation that was higher than the headwater elevations illustrated here in pink. Our capacity to drown down this basin by gravity discharge is reduced when we have the tailwater elevations higher than the headwater. So we basically can read here in red, in the bottom red here, we can read zero discharge from the basin in the gravity S13 structure as shown here. And also pre-storm discharges were only occurring because we had a pump in this basin. We have a pump in this basin. So we can see here discharge in green. After the rainstorm, so this portion of the chart here is showing the rainstorm occurrence and how the system was operating. But after the rainstorm, the gravity discharge was again interrupted. So you see a little bit of discharge here from the gravity and then zero again, because the tailwater elevation again was higher than the headwater elevation. So we had to install a temporary pump here, illustrated in blue. And this was on for about 18 days. Most of our control structures are not equipped with a pump to assist in discharging when those tailwater elevations are higher. And then, of course, we result in limited gravity discharge. The issue is that the faster we can drain our canals and move water away, the faster we can reduce the flooding impacts in all the secondary and tertiary systems. And with increasing sea level rise, we have been observed higher tailwater elevation and increased time that our control structures are closed and the discharges are zero. It's important to note that significant rainfall events occur before the arrival of Tropical Storm Eta, which contributed to extreme wet antecedent conditions. We see rainfall totals between 200 and 300% higher than the historical average for the month of October at the core of the Tropical Storm Eta rainfall event here in the Lower East Coast. And even more than 300% here in the map on the right, in purple here, in most of the regions, and this was during the month of December. The major impact, another important and significant information to share beyond the significant rainfall events is that we also had a very intense high tide season in 2020. This illustration shows the predicted peaks that are published by NOAA every year, and this was between August and December. So let's see what really occurred. Those were the predicted peaks, and then the next slide here will show some of what we are observing. So in Fort Lauderdale, back in September, thanks Dr. Gassman for this information, the observed high tide was significantly above the predicted tide. The predicted is the blue one, and the red is the observed. And it also remained above the threshold for flooding in low-lying areas of the city. So this horizontal red line here is really the threshold that tells the city we are having significant flooding. And this lasted about 5 hours every day during those high tide events. This image here, it's a little bit complex, but it summarizes all the records that we have for high tide observation. So the black is the maximum historical, the bottom red is the minimum historical, and then we have also the green showing the average daily tailwater stage between 86 and 2019 at the S20F structure in Miami. The pink line plotted on top of that is the 2020 high tide observations, and we are going to zoom into that in this next slide. And so what we can observe in this pink line is that the 2020 exceeded the historical maximum by over 1 foot for that period in September, and again towards the right side of the chart here, above 1 again in October. Another very interesting observation is the relative percent time that those gates were closed during the same period in this same location. The green line shows the average hours per day, and the pink line, the 2020 observations. So the bars clearly demonstrate that a significant number of hours, way above the average, day after day, when the gates had to be closed and our gravity capacity was limited, discharge capacity was limited. The same was also observed in many other locations along our coast. And of course, with all these record numbers, we were bombarded by many news reporting critical flooding conditions in several locations. And these and many other references quickly point to the association with climate change as the main factor for those extreme occurrences. And then we as water managers decide, and we understand that we have to dedicate more time, extra time, to really understand more in depth how significant was this? Like, how significant was the 2020 events compared to our records? What are the impacts that are being observed in South Florida in general? And if and how we can associate scientifically these impacts with climate change. And a very important question, are these events part of a long-term trend in terms of magnitude and frequency that would impact the way we manage our systems today? In this context, it becomes evident that the development of those metrics that can help us to answer these and many other questions is really important. As mentioned, the district is an agency with a very long tradition in managing this robust network and in monitoring data, and also in making these observations available to the public in general. Therefore, the objectives of this current effort being shared with you today is really to track and to document these long-term trends and shifts in observed data, to advance the understanding of climate change and how this can be influencing these occurrences and our mission in general, to report and communicate those results in the associated science, and later use these results to support the assessment of future conditions and start developing uniform guidelines and design standards. I'm bringing this slide from a presentation that I watched a few days ago as part of this hyperfacet project. And it's actually one of the outcomes that focus on typologies of actionable climate information and its use. The main message that I got from this presentation is that climate information is the fundament to advance resilience action and also to support partner engagement. I'll be happy to share this entire slide set with you upon request. It's a very interesting research. So the potential benefits that this effort will be bringing, not only to the district, but also to our partners, is to have a strong planning capacity. The results will also serve to better substantiate modeling assumptions and risk-informed decisions, including smarter investments in our infrastructure development. And this work will also contribute to more educated and engaged stakeholders and partner agencies in water resiliency aspects, as well as the enhanced resilience of district projects in general. This initial work has been developed through an internal team effort to advance the scientific and the technical understanding of these trends and also associated considerations. This group produced an initial report that contains robust data at some district locations, and these locations were selected to exemplify observed trends that occur throughout South Florida. We included just a few examples here so far. The team also did an extensive research to evaluate multiple already existing efforts and tools advanced by organizations like the Southeast Florida Regional Climate Compact. This slide illustrates the latest unified sea level rise observed trend at the past 30 years, as well as future unified sea level rise projections. The trend is here at the very left bottom portion of the chart, and then the projections, of course, are here. EPA also published climate change indicators, here showing charts of the average drought conditions on the right and extreme one-day precipitation events. Despite being a more static graphic, please note that there is relevant information being shared. The image on the left displays an upward trend in extreme precipitation in the continuous 48 states. Another database is the Usgcrp indicator platform with county-wide charts and maps for a series of key climate indicators and associated metadata. This is the basic data that is used for the national climate assessments. And on the right, I pick one chart here to illustrate the annual global average surface temperature difference from the 20th century average for the land and the ocean. And again, as we can see, we also observe an upward trend. Here we illustrate data from NOAA, which maintains truly one of the, I believe, the most important repository of climate data in the US. This climate division portal here is very intuitive, allows the user to interact to obtain tabular mapping data. We can also choose city, county, division, state, regional, national, and even global levels. And this chart on the right here, I picked as an example, and we can observe here an upward trend in the Miami-Dade minimum temperature records. Finally, one last example is from the Climate Central. This is an independent organization of leading scientists and journalists researching and reporting facts about our changing climate and its impact on the public. Their website contains really illustrative graphics and nice visuals, which can also help us about the importance of really communicating what we are observing. So good. After looking at these and many other great examples to leverage what are the existing resources and tools, the work group start listing a series of potential metrics that we have, trying to focus on data that is managed by the district, which also would provide long-term observations. I apologize for the small font on the left, but here is just an illustration of the large set of available data that was initially evaluated by the work group. So from these 50 plus initial metrics, a total of 15 were selected as an initial priority set to represent this key observed data related to sea level, groundwater, hydrology, water quality, and ecological aspects. At this time, I'm really happy to invite our technical leads to give you a brief overview of some of those key metrics and share some of the initial results. Thanks, Dr. Desalagne, for joining us today. And he will start with the tailwater elevation data. Thank you, Tibet. Please let me know when you want me to move your slides.
Thank you, Carolina, and good morning, everyone. And Tibet Desalagne from Hydrology and Hydraulics Bureau. I'm going to briefly describe the metric on sea level that is relevant to our coastal structures. And the district's coastal structures are at the outer boundary of the water management system, and they control the movement of water from inland to ocean and vice versa. And they are also critical in the flood control as well as prevention of saltwater from migrating towards inland. As Carolina mentioned earlier, these structures are mostly gravity driven, and they need a positive hydraulic gradient to move water out of inland to the ocean. As a result of this, their discharging capacity will be reduced when the tailwater condition is higher. And this is particularly a concern in coastal structures in Miami-Dade and Broward counties, where the design height across these structures are relatively low. So at higher tailwater conditions, as demonstrated in Dr. Moran's talk earlier in C11, in order to supplement the lost discharging capacity of gravity structures, we need to add forward pumps. And currently, the district has a permanent forward pump at only 2 locations, but working actively to expand that feature to other coastal structures. And the sea level metric will look at statistical analysis on water level, time series data at coastal sites, as well as NOAA tidal stations. And one of the analysis is going to be done under this sea level metric is a trend analysis on instantaneous water level data at different time scales, daily, monthly, and annual. And the result of this metric, together with other initiatives under the district, such as the flood protection level of service, will assist in identifying the most vulnerable structures and also to plan mitigation measures such as forward pumps. Next slide, please. The metric will look at two sets of data. One is water level at our coastal structures, and the other is at NOAA tidal gauges. And these two graphics show the water levels at coastal structures. And the one in the left is the water level daily maximum at coastal structure S27, the ocean side. And the vertical axis is the daily maximum tailwater stage in feet NGVD. And the horizontal axis is the date. And as you see in the blue trace, the daily maximum tailwater stage fluctuates from day to day. However, there is an increase in long-term trend, which is not obvious from this chart. And looking the chart in the on the right, that is at a larger time scale, monthly, at coastal structure S22 in Miami-Dade County. And the vertical axis is the monthly mean in feet NGVD 29, and the horizontal axis is years. And the blue circles represent the monthly mean data points, and the red line is the trend, long-term trend over the period of record. And as you see here, in all of the months, the tailwater stage showed an increasing trend. But it is worth to mention that tailwater can be affected by different factors, such as rainfall and the structure operations. Therefore, the metric also will look at to identify or quantify the change in tailwater attributed to change or rise in sea level. Next slide, please. The metric will also look at the tidal stages and high tide events or extremes. And these are samples. The one in the left is from Florida International University, the daily maximum stage in centimeter NAVD 88 at Virginia Key Station. And the left vertical axis represents the year, and the horizontal axis is the month. And the color from light blue to darker blue represent the daily maximum stage, and the burgundy color represents the king tide, and the vertical axis to the right, the numbers represent the duration of those high tide events. And as you see here, this is a good way of presenting data. One can clearly see, for example, if we focus on the burgundy color, we see that the high tide events occur from September through November. And also a closer look at the numbers on the right, which represent the duration of high tides. One can see that the longer duration high tide events occurred after 2015, starting from 2015. And the figure on the right shows the monthly means at NOAA Key West Station for the period of record. And the vertical axis is the water level in feet above mean sea level, and the horizontal axis is the date. And as you see here, the mean monthly stage has an increasing trend, which is indicative of the sea level rise. And as part of this metric, we are planning to conduct this analysis at all of our coastal structures, and also tidal, NOAA tidal gauges relevant to our region. And that's all I have for sea level rise metric. And now I turn over to Karen Smith on her talk on groundwater and stage metric. Karin?
Good morning, thank you. Hi, this is Corinne Smith. I'm in the Water Supply Bureau. I'm the Lower East Coast Water Supply Plan Manager, and I'm going to talk about groundwater stages and saltwater intrusion. And I just want to quickly go over when you're looking at sea level rise, the red dashed line on this graphic shows you what happens to water levels when the sea level rises. So as the sea level rises, the saltwater front, which is the angled below ground piece, moves further inland, gets closer to wells that might be on the coast, and they might start pulling in salt water. It also raises the water table, and that causes issues with flooding because now you have less storage capacity in the drainage system for at the houses. Next slide. So I decided to just go see if I can see, oh, no, go back. Yeah. Carolina, can you go back one? Yeah, thank you. I wanted to just see if I could find that happening in the monitor data. So on the left-hand side is the monitor data that we have in our DB Hydro database. Blue being wells that are sampled by the district, yellow being information that we get from permittees, and then green being the USGS data. So I looked at a spot in Hollywood where we had a series of wells that went from inland out to the coast and then had a structure, a water control structure with a downstream stage that's just off of this map to the southeast, and wanted to see if I could see that, what I showed in the last graphic happening. Okay, next slide. So the bottom green is the downstream stage at the structure, and you can see with the little dotted line, that's the trend that it is, that that water level is rising, indicating that there's some indication of sea level rise at in this area. And then the rest of these are a series of wells, and the legend at the bottom shows you from going inland out to the coast. So G1226 is the furthest inland, and F291 is at the coast. And I want to point out, though, that at G1226, that's in the Hollywood, in an area near the Hollywood well field for the public water supply. So there is some drawdown because of that, although they have cut about half of their pumpage there because of the movement in of salt water and have moved to the Florida, and so there's less than there has been in the past. But as you can see, the lowest levels are inland because of the pumpage. The highest level, if you look at 2010 at the left side of the graph, is out at the coast, which is normally not what you would think, because you would think that the groundwater levels would be higher inland and going out towards the coast. But this is what we're seeing in this cross section, is that water levels are raising up at the coast. This is just the last 10 years. And if you look at the blue dotted trend, you see that that one's flat all the way across. And that's because at the very end in 2020, there have been some really low water levels, and that has kind of changed the trend, the 10-year trend. But if you look at the other three, you can see that all three of them are going up at basically the same rate as the that you see at the downstream stage gauge. So as the water levels are coming up with sea level rise, the groundwater levels are definitely showing that trend also. Okay, next slide. Next slide? Okay, thank you. All right, so the map on the left, on the right, is Broward County, and I'm showing you the green dots being the public water supply well fields, the squiggly lines being the inland extent of the saltwater intrusion. Now, this is not the saltwater all the way up at the top. This is down at the bottom of the aquifer because it comes in as a wedge. It's the furthest inland extent of 250 milligram per liter water, which is the point at which it's not not drinkable. These lines are every 5 years, the Water Supply Bureau creates a new line, looks at all the data. The most recent one is in red, and that's 2019, and that's showing what we feel is the current inland extent of saltwater. And as you can see, there's wells that are pretty close to the line. So looking backwards, I look to see, well, how many wells in the public water supplies in the district, East Coast, have been abandoned because of saltwater. And I only looked back 20 years, and I might not have caught all of them, but this is a list of ones where they did report to us. They took them out of their permits, and they indicated they were because of saltwater. So in water supply planning, as we do each water supply plan every 5 years, we also look to see how the utilities are doing in relation to saltwater intrusion on the coastal regions. And we have we look at all the utilities, and we have a metric for that. We call it either utilities at risk or utilities of concern. And the at risk are near the front, but they don't have any, that's their only source. That's their only well field. And the utilities of concern have a well field near the coast, but they also have access to an further inland well field, or they have an interconnect to an inland well field, or they've gone to the Floridan. So, so looking forward, so we look, and you can see the results there. Looking forward, we would like to be able to make maps that show color-coded what the wells are, what the monitor wells are doing, and also what the actual permitted wells are doing. And this graphic on the right only has the public water supply, but there are agricultural wells, and there are landscape wells, and there's a few, there are wells on the east side of those lines that are shallow and are still able to pump, but it becomes more difficult as the front moves in, as you saw in that first graphic. So we would like to, USGS has this wonderful mapper thing that you will see as a presentation later in this whole presentation today. And we would like to duplicate something like that does our permittee data and our own data that we collect by district staff. And we'd like to also have a map of all the where wells have been abandoned because of saltwater, where they're at risk, and then a link to a table of how close are they to the front, where's the nearest salinity control structure, what's the water level in that basin, is it high enough to keep them protected from saltwater, or is it almost the same as the sea level? And then we also have the Biscayne Aquifer Mfl, which is in basically Broward and Miami-Dade counties. And it's right now in prevention strategy, and we'll continue tracking it. It's supposed to, you're supposed to have a minimum water level to prevent the movement of saltwater inland to the point where existing users can no longer use their permitted wells, their source. So the way we do that is we keep water in the canals to have a high headwater at the salinity control structures, and we monitor the saltwater movement. And because we're seeing movement, and we know this with saltwater and with sea level rise, things are going to change. We are going to have to relook at that MFL, considering sea level rise. And that is what I have. And so I'm going to hand you off to Ala Ali, who will talk to you about rainfall.
Ala, we cannot hear you. Can you please unmute your phone?
Yeah. Can you hear me now, right? Hello?
Yes, we can hear you. Thank you.
Everybody. Sure, thank you. Good morning, everybody. My name is Ala Ali. I'm a chief engineer with the Hydrology and Hydraulics Bureau. Today's topic is rainfall. Next slide, please. Yes, before I talk about this charts, let me tell you, as everybody or many of you know, that rainfall is the main or the primary driving component of the hydrology in South Florida. And the district has an extensive network of rainfall, and we have performed extensive studies for rainfall studies. We have a lot of rainfall studies that we always refer to in our operations and our modeling and all other studies. For the purpose of resiliency, we really, the existing studies, we are interested in two things. One is to extend it to the latest and the greatest rainfall data set. Two is to explore variables that they are more suited for the resiliency studies. We are interested in knowing whether we have a trend in rainfall data, and two things here come to mind. One is the overall average statistics of rainfall that create volume in the system. Are we having increasingly or an increasing trend of that average statistics? The second one is, how about the frequencies of maxima? If there is also a trend in those, I would say, low frequency data or data with high values or large return periods, are they also on the increasing trend? We relied on two things. One, the district extensive data set, data that we created the primary data set for all our models, which is called the rainfall binary file. We have extensive data set that have undergone extensive QE/QC, and then we consider those 14. If you to the right on the map of South Florida, you have here 14 operation areas, and those 14 operation areas, we are interested in knowing those trends on each area. With that being said, if you look at the left, these are only sample of the study. The entire study is available upon your request. This study basically has performed what we call trend analysis on monthly data. We want to see if the monthly data has some trend. What monthly data means that the overall sum of rainfall for each of those individual 14 areas, and this is from January all the way to December. That chart that you see here is only for August. So that chart saying that the rainfall sum for the month of August from 1914, year 1914, all the way to 2018, how would that data tell us anything about future trend? We performed man-candle test on that, and as you see, the areas with red represent increasing trend. The areas in green saying there is no any increasing or decreasing trend. So if you look at the East Caloosahatchee, which is here, which is, if you look at the chart to the right, the graph to the right, you will know which one I'm talking about. So in East Caloosahatchee, in the lower Kissimmee, and in the southwest coast, as well as the Palm Beach counties, also Martin, St. Lucie, you will see there's an increasing trend of August rainfall, which will put some flag on how we're gonna accommodate that in the future. Of course, the picture will not be complete unless we look at the other individual months and relate the month to the region, and the story even will be more coherent. And like I said, feel free to basically ask me for the whole study, and hopefully a full documentation will be available soon. Second slide, please. Second slide. Yes. Okay. This is basically what we did. Okay, we showed August as a sample of the months, but now we combined the rainfall over in June, July, August, and September, and we call this, okay, this is the overall wet season rainfall in the summer. What kind of trend do we see? If you see, the persistence here was in the East Caloosahatchee, the southwest coast, and the Martin, St. Lucie. You can relate that to the area to the right. We see also increasing trend on those areas. Next, please. Okay, now we talked about the behavior of the average as a key statistic to rainfall. Now we're going to be talking about the rainfall maxima. Okay, so what is that? Basically, we study the rainfall maxima. What is that? Basically, if for each of those years, we have 105 years of data. For each year, we identify the maximum rainfall event over 5 days. And we have 105 data points. Based on those data points, we perform frequency analysis. Okay, and this frequency analysis, we take the 2-year return, which represents more or less the average behavior of 5-day maxima. I hope you guys are following what I'm saying here. So basically, the 5-day maxima, we perform the frequency analysis for it, and then we take the 2-year return period, okay, which more or less the average behavior of the 5-day maxima, and then we perform a trend analysis to that. And when you look at this, you will see that most of the stations, most of the areas do not exhibit any trend, but for Big Cypress and for the Southwest Coast, again, I have an increasing trend. So this means that the characteristics of the stochastic process or the random process or the process that generate those rainfall events that you can say here, this one is like for example, this is like a 2-day year return period. The 5 maxima, we expect more extreme events that on the increasing trend in Big Cypress and Southwest Coast. Of course, the overall study would give us a more coherent story on this, but certainly there is a flag or there is a concern that would definitely be an important component of the resiliency study that would really create some sort of mitigation or precaution that we have to take in order for us to move with any studies related to rainfall for the purpose of resiliency. With that, I would like to turn the floor to Kevin to talk about other hydro management data. Thank you.
Thank you, Ala, and good morning, everyone. This is Kevin from the Hydro Data Management section and the H&H Bureau. Today, I'm going to give you a brief view on the trend of evapotranspiration. Next slide, please. Besides rainfall, evapotranspiration is another most significant component in hydrological cycle, and it has a magnitude comparable to the rainfall. As its name indicates, this metric includes 2 parts: the evaporation from ground surface and the transpiration from the plants or veggies. The first chart shows the long-term monthly rainfall versus ET at the districts. The blue columns for rainfall and the brown ones for ET. We usually break a year into wet and dry seasons based on rainfall amount. The wet season is from May to October, 6 months, and they all have the rainfall greater than 4 inches per month. But really in the 4 summer months, from June to September, stand out with rainfall greater than 7 inches per month. So sometimes we call the May and October are transitional months because they are not that high enough. The dry season is from November to the next April, 6 months also, and their rainfall is about 2 inches per month. In general, rainfall is greater than ET in wet season, and rainfall is less than ET in dry season, except May, which is the start of wet season. However, ET is also picked up in May. ET is also picked up in May. The second chart shows the monthly difference, ET minus rainfall. So with this chart, and in terms of the net water budget or net water balance, you can see the wet season only 4 months, from June to September in the summer, and the dry season lasts 7 months, from November to next May. While in October is a neutral month because it's in balance just between rainfall and ET. Next slide, please. For the resilience study, we selected 4 data sets of ET. They have a period of record varying from 60 to 23 years for trend detection. 3 of the 4 data sets are about pan evaporation, which are the first 3 lines at the top in the first chart, the big chart. And then the rest of 1 data set, which is the blue line at the bottom, is derived ET from USGS in cooperation with the University of Alabama. To the right-hand side, the map shows the locations of the 3 evaporation pans. 2 of them inland, which is the S7 and the S140, are maintained by district staff. And the one by the east coast is from the city of West Palm Beach. As you can see, all the data, the 4 data sets shows an upward trend in which the 3 lines, green, orange, and blue, they share a similar slope of change. The second, on the smaller chart, shows more details at the station S7, which has the longest period of record back to 1961, or 60 years ago. And this station is probably the best maintained one in the field. The annual data are presented at the upper portion of the chart. The orange dots are from the data before 1985, and then the green ones are for the years after till now, till last year. The seasonal data are shown at the low portion of the chart. The blue ones for wet season and then the brown ones for dry season. So for this single station, we got 4 series of data presentation from different aspects or angles, and all of them show an upward trend. You may notice the wet season has a steeper slope than the dry season. However, statistics, which is the MK test, still prove the trend from the dry season. Let's look back to the first chart, the big one. The 3 pan evaporation data sets are point data at a specific sites, as you can see in the map. While in the USGS data in blue at the bottom is the area data averaged over the entire district. The USGS data is about the potential ET calculated with insolation on radiation data, which derived from the satellite image, and its formula was calibrated with ground stations. So as we can see, these 4 data sets, they all collected or monitored independently. So their results can verify or cross-check with each other, which means a high confidence in a trend detected, which has been happening in the past 30 or 50 years. So that's it about the ET. And our next presentation is given by Nanette on the water quality.
Thank you, Kevin. Good morning. I'm Nanette Urikkanen from the Water Quality Bureau. This morning, I will discuss our initial analysis of the water quality metric. For this presentation, I will focus in on specific conductance, which is a conservative parameter and one of the most frequently measured water quality parameters. We chose specific conductance as a water quality metric because we expect it to be a good indicator for climate change. The results I will present today will illustrate the unique challenges in detecting climate change influences on water quality. Next slide, please. The analysis presented is based on 48 years of data collected as grab samples from 6 monitoring stations in Lake Okeechobee. The 6 stations were chosen because of their long period of record. Data were summarized on a monthly basis and were used to establish a long-term trend. Climatic conditions such as droughts and tropical events were also identified. And by the end of my presentation, I hope to offer an interpretation of the observed trends in specific conductance. Next slide, please. So the plot that you see shows specific conductance level in Lake Okeechobee decreasing significantly over the 48-year period. The trend line is shown as the blue line on the plot. The y-axis represents the monthly mean specific conductance, and the x-axis gives you the monthly time series. Specific conductance levels at the start of our study period were higher than normally expected for Florida lakes. In more recent years, specific conductance levels appear to be more comparable to levels that you typically see in lakes around Florida. The plot also shows how specific conductance varies seasonally and in response to climate events. For example, we have higher specific conductance levels associated with droughts and dry seasons, and lower levels occurring during wet seasons and following tropical events. Next slide, please. So when we look at our data on a seasonal level, we can see the same downward trends across all the months. This is interesting, as even the dry months are showing the same trends. So are these trends associated with climate change and simply reflect dilution in response to increased rainfall or runoff? Or are other factors influencing the trends? Could the high specific conductance levels observed at the start of the period of record reflect influences from sources such as connate seawater? Well, to answer these questions, we need to take a look at the relationship of specific conductance and parameters affecting it. Next slide, please. At this point, I would like to provide you with a little background on specific conductance. It measures the ability of water to carry an electrical current and is affected by the types and amounts of ions present in solution. The plot on the left shows a highly correlated relationship between major ions, in this case, cations and anions, and specific conductance in Lake Okeechobee. The units that I'm using are milliequivalents per liter, and the reason that I've used those units is to account for the charge of the ions. Cations are positively charged, anions are negatively charged. One thing that the relationship does not provide is information on whether the ionic composition remains constant across the specific conductance regime. In order to understand and characterize the ionic composition, we are going to take a look at a couple of visual tools to help us along this path. Next slide, please. Shoulder and stiff diagrams are typically used to visualize ionic compositions that are present in aqueous solutions. The graphical shapes generated from both tools can provide us with useful information regarding dominant ion pairs and changes in ionic composition. The Shoulder plot shown on the upper right uses line plots to represent differences between cation and anion concentrations, while the stiff diagram generates polygon shapes based on concentration of ion pairs, as shown in the diagrams on the lower right. And you can see that as the dominance of ion pairs changes, the shape of the polygon changes as well. To identify potential changes in ionic compositions for our analysis, the specific conductance levels were statistically grouped based on percentile ranges, and the associated ion concentrations within these ranges were averaged. And these results are presented in the following slide. Next slide, please. So if we look at the left plot, which is the Shoulder plot, it shows that the ion concentrations across a given specific conductance range. The top line plot identifies ionic compositions at the highest specific conductance range where both sodium and chloride pairs are more dominant. As the specific conductance levels decrease, the shapes and dominant ion pairs change, with calcium bicarbonate becoming more dominant at these lower specific conductance ranges. Overall, the data shows a shift in ionic composition in Lake Okeechobee over the specific conductance regime. This is, I think, more clearly displayed with the SIF diagrams on the right, and you can see how over the specific conductance ranges, the shape of the polygon changes, reflecting the change in dominance from a more sodium chloride to a more calcium bicarbonate. Next slide, please. So if you go back to our time series plots that we saw earlier, we can observe the decadal shift in ionic composition is depicted by the stiff diagrams at the top and the associated changes in specific conductance. We also looked at a couple of ion ratios. In the middle plot, we have sodium to potassium ratios, and we use these to attempt to identify potential sources. During the first decade, sodium-potassium ratios were higher, averaging around 22, and approached a ratio of 46, which is representative of seawater. More recent sodium-potassium ratios averaged around 8 and are more typical of surface waters, surface freshwaters. The sodium-potassium ratios from 1973 to 1982 suggest that that period may have been influenced by a more marine-like source, such as connate seawater. Additionally, we looked at sodium-potassium ratios, and just as you can see in the stiff diagrams, the sodium-potassium ratios show that during the first 3 decades, sodium was the dominant cation in Lake Okeechobee, after which calcium became the dominant cation in the lake. Interestingly, both of these ion ratios suggest that a shift in ionic composition may have occurred after 1994. Next slide, please. So to summarize, atypically higher specific conductance levels were observed in Lake Okeechobee earlier in the period of record. A significant long-term decrease in specific conductance was observed. The change in specific conductance did not appear to be a result of simple dilution, but appears to correspond to a shift in ionic composition from a sodium chloride source to a more calcium bicarbonate source. Sodium-potassium ratio suggests that the elevated specific conductance observed in the early period may have been affected by a more marine-like source, possibly upwelling of connate groundwater. Both the sodium, calcium, and sodium-potassium ratio suggest that the shift in composition may have occurred after 1994. This evaluation shows that linking changes in water quality to climate change is very complicated and may be affected by multiple factors that can exert a greater influence on water quality than climate change. That doesn't mean that climate change is not influencing water quality, but flushing it out may be more difficult. Presently, we are looking at using more robust data sets, such as the continuous recorded data, water quality data that the district has to track climate change influence on water quality. Unlike grab sample data, continuous water quality data should better characterize daily changes. And now I turn over the presentation to Carlos Coronado, where he will discuss soil subsidence.
Carlos, we cannot hear you yet. Are you there? Can you mute your mic, please? Let's give a few more seconds to check if Carlos was able to open his mic. Can you hear me? Yes, I can hear you, Carlos.
Thank you. Thank you very much. I'm sorry about that. Hi, good morning. My name is Carlos Coronado, and I'm lead scientist in the Applied Sciences Bureau. And today I'm going to be talking about soil subsidence. Next slide, please. So we are using soil elevation and soil subsidence as a metrics to assess the effect of sea level rise in coastal environments. But before we can talk about soil subsidence and soil elevation, I'd like to describe what we understand by soil subsidence or pit collapse. So to do that, I'm using this conceptual framework that was published by Chambers and her colleagues in 2019. And it's a wonderful framework because it explains very well all the process from a healthy plant community shown in panel A. So in the panel A, a healthy plant community, it acts as a net carbon sink. And also, the most important thing is the structure of the soil when the plant community is healthy really leads to an increase on elevation. However, any coastal plant communities are exposed to different stressors as shown in panel B. So those stressors are grouped into acute and chronic. For today's presentation, we are more interested in understanding the effect of sea level rise on healthy plant communities in coastal areas. What happens with a healthy plant community is affected for any of those stressors. The first thing, or the last thing that happens, as shown in panel C, is that the coastal vegetation dies. And then when the vegetation dies, the site becomes a net carbon source for one point, and the other one starts losing elevation because the strength of the soil is lost. So to explain what happens when the plant community die and start losing elevation, panel D shows 4 different mechanisms that trying to explain the loss of elevation when the plant community dies. The first 2 mechanisms explains the physical of the soil, the pore space compression and soil organic destabilization is related to the physical of the soil. The third one, which is the parenchyma compaction, it explains how the roots of the plant community that is dying or is dead is lost. And the last one is the shift of the carbon balance, moving from sink to a carbon source. So using those 4 mechanisms to explain what happened in coastal environments, that leads to a loss of elevation that in the panel E shows as a pit collapse. Here I want to express that pit collapse is a specific description of soil subsidence. Pit collapse is described as the loss of elevation in highly organic soils, but it's also an elevation. Next figure. Thank you. So in this figure shows where for the last 20 years we've been monitoring the change on the elevation in coastal environments. So we've been working in the area around Taylor River Slough, is the northeast region of Florida Bay. And we have sites all along that coastal environment. And we have grouped our sites in 2 different groups based on the hydrology of those sites. The first group is the permanent inundated group, and the second one is the frequently inundated group. And the idea behind this is to want to understand if there is a difference in elevation change between those 2 different mangrove types of environments. Next one. So how can we measure soil elevation change? The panel on the left shows the methodology that we use in the field to measure elevation change. The figure shows two components. The first one is the SET, the soil elevation table, that measures the elevation change all the way from the surface of the ground all the way into the base of the pipe that is shown in these figures. So all the measurements that we do in the field measure the change on the elevation all the way from along that profile. The little white figure there, it shows a marker horizon that we use to estimate the accretion, which accretion is how much the organic matter that is deposited over time on top of the marker horizon. The combination of both the sets measurements plus the accretion coming from the marker horizon gives you an indication how good or how bad those sites are changing in elevation. To illustrate how we use that data, the two panels on the right show a theoretical sites to show how we use that data. The panel on the top is a theoretical site that shows that both the elevation change in the vertical accretion are positive over time. The interpretation of that particular figure is that for that particular theoretical site, the subsidence rate is very low. In contrast, the panel at the bottom shows the opposite. The difference between both the accretion line and the elevation line is bigger, as shown by the double arrow in this figure. For this particular theoretical figure, the subsidence rate is higher and not only is losing elevation. So the definition of soil subsidence is shown here. Soil subsidence is a process in which there is a loss of soil strength and the structural integrity that contributes to a decline in vertical elevation below the lower limit for plant growth and natural recovery. Next one. So we are showing the results of our monitoring sites that we've been doing for the last 20 years. So the panel on the left, it shows the results for all the sites that are frequently inundated. We have 5 different sites, independent sites. And then this particular, the data from the frequently flooded sites shows that elevation change for the last 20 years, or at least from 1997 to 2020, has changed 3.9 millimeters per year. And the accretion in those environments is 2.1 millimeters. The difference between both the elevation change and the vertical accretion shows that these particular environments, there is an increase in elevation of 1.8 millimeters per year. The figure on the right shows the results from the permanent inundated or flooded sites. And there is a contrasting difference. Here, the elevation change is only 1.7 and the vertical accretion 1.9, with a soil subsidence of 0.2 millimeters per year. So we can see that the importance of hydrology to understand how the different mangroves are responding to the hydrology that they are experiencing in the coastal environment. Next one. Next figure. So to summarize, here are showing 2 different pictures in the field. The top on the left, it shows a freshwater environment in the Everglades, and you can see how the elevation has been lost in this environment. And the picture on the right is a mangrove site. Also, you can see how the mangroves have died, and the death of those mangroves are related to the tremendous hydrology that they've been experiencing over the last years. So to summarize, the point number 1, we say that even though hydrology is very important to observe an increase in elevation, that emphasizes the importance of below ground processes such as root production and decomposition on the trajectories of elevation change. Point number 2 indicates the summary of the permanent inundated sites. And for these particular sites, those sites, as we saw, there is a subsidence rate, and those sites, they are not keeping up with current sea level rise. And we believe that the reason behind that is that there is a very forest structure, the low production and salt intrusion are among the factors controlling this trend. Finally, all the sites that we've been monitoring for the last 20 years in northeastern Florida Bay, they are not producing enough soil to keep with current sea level rise, and suggesting that these mangroves in South Florida Bay, in South Florida, are vulnerable to sea level rise. I think this is it. The next speaker is Tara Root. Thank you very much.
Thank you. Thank you very much, Carlos, for your great presentation. Let's all take a break. We went through a lot of information so far, and I really appreciate the great content that was shared with all of us now. Thank you very much for all the technical leads here today for the valuable insights. So after reviewing these those examples that were presented now, we can summarize basically 3 main outcomes that we were able to achieve so far with this work. So we have an initial set of prioritized metrics. We have recommended approaches to do the statistical and the associated data analysis. And we have alternative illustration options to display and start communicating those results. Our next steps really include the implementation of those metrics district-wide, really finding all the locations where we can illustrate those results. But before I provide any details about our plan to implement those metrics, I would like to invite Dr. Tara Roots from USGS to present an overview of this very interesting tool that was developed by USGS to report on water levels in salinity. Thank you very much, Dr. Roots, for joining us today. I'm giving you not only the mic, but I think I'm also giving you control to the screen.
Okay. Let's see. Let me just check if I have control. Not yet.
Yvette, can you please confirm if Tara has control? Otherwise, I can try to pass, but. Are you able to control?
Yeah, no, so I don't have control. I'm fine having you control whatever works best. Just let me know if you want to control.
I gave up control and I'm not sure if I can recover without Yvette transitioning back. Okay, I have control again. So I know how to pass your slides there. Let's go.
Okay, all right, sounds good. Well, thank you very much for having me here today. I am a hydrologist with the U.S. Geological Survey. I'm with the Caribbean Florida Water Science Center, and I'm located in the Davie office. So the USGS collects a lot of similar types of data and does analyses that are very similar to a lot of what you all have been discussing here today. And we have an interactive website that makes that data and technical information accessible and useful to end users. That website is called our Water Level and Salinity Analysis Mapper. And today I'm going to present just a brief overview of that site as an example of some possible ways that these types of data and technical information can be presented. The reason we're all here and participating in this workshop today is that there are these wide variety of drivers and stressors that are impacting the sustainability of water resources. Scientific and management agencies like the South Florida Water Management District and the USGS are collecting tremendous amounts of data to determine how hydrologic systems are responding to these stressors and also to predict how hydrology is going to change in the future. But that then leaves us with the question of how do we make all this data we collect useful for water resources management? So to aid water resource managers, who are the ones making the decisions about how to prepare for and respond to these drivers of hydrologic change, the USGS provides data like those shown in the table here on the right. We analyze those data using some of the same types of analyses that you all have been discussing here today, like historical trend analyses and frequency analyses. And we present the results of those analyses using visuals. So these three things, the data, the analyses, and the visuals, are what make up our water level and salinity analysis mapper. So now what I'm going to do is just show you some screenshots to present some of the highlights of features of the water level and salinity analysis mapper. As you can see here on the right, very similar to what you all have in DB Hydro, it has an interactive map interface that allows users to search for specific sites and also to filter by type of site or type of data. And users can select to have the map display the result of our trend analyses for either water level or salinity data. The symbols on the map provide a visual indication of whether the data values are trending upward or downward over time. And users can select to either display recent trends, for example, over the last week, or longer term trends from the last 5 years or 20 years of data if there are enough data available for those longer term analyses. Users can select to have the map display the results of our frequency analyses, which is what indicates how current data compare to historical data. And for this, we use different colored symbols to indicate whether the current value is higher than, similar to, or lower than the historical median. So this is an example of how our salinity data is displayed on the map. Some of this data that you're seeing on the map here is very similar to the type of data, and also the map visualization is similar to that that Corinne Smith discussed in her presentation. The symbol color on this map indicates chloride concentration. So you can see the wells that are red, that are close to the coast, are salty with chloride concentrations greater than 1,000 milligrams per liter. And then just inland of that are wells with blue symbols, and that blue indicates that the water there is still fresh. Users can toggle to see the approximate inland extent of saltwater intrusion in various years. So here on this map, the inland extent of the saltwater intrusion line in 2018 is displayed. When users select a site on a map, a pop-up window opens that displays the most recent data value, the magnitude of recent change, as well as the long-term trend directions. And from here, clicking on that site number will open up a page with several time series graphs and tables that display further details of our analyses. This slide gives some examples of some of the graphs and tables on that site page. The tables can all be downloaded as text files from this page. And for the next couple of slides, we're going to zoom in first on this middle graph and then on the right-hand graph and use those as just a couple of examples of our graphical products. So here we've zoomed in on that middle graph from the previous slide. This is a time series graph with the black line showing the last 2 years of daily water level data. On this graph, you can see how those data from the last 2 years compare to the historical range in the data, which is shown in the blue, and also how they compare to the mean of the historical data, which is shown in yellow. For this particular site, I think there's a 26-year period of record. So this graph is just another visual that lets the user see how recent data compares to the historical record. And this second graph that we'll use as an example shows chloride concentrations versus time over the entire historical record for this well. This well has a record going back to about 1960. And you can see in the blue symbols that the water in this well was fresh through about 1990, and that the symbols turn yellow, which is an indication of brackish water. In the early 1990s, that indicates that the saltwater front was passing through this well in the early 1990s. And where the red symbols start in about 1995, the saltwater front had passed this well and chloride concentrations exceeded 1,000 milligrams per liter. You can also see on this graph the two trend lines, one showing the slope of the 20-year trend and one showing the slope of the 5-year trend of the data. All right, so that's a quick summary and a few highlights of the features on our water level and salinity analysis mapper. It includes an interactive map and search and filter tools. Also includes access to data tables and the results of our analyses. And there are a variety of visuals, both on the map and in graphical form, that display temporal trends and provide a comparison between recent data values and historical data. You can see the URL for the water level and salinity mapper here in case you want to explore it in more detail than I have presented here. Thank you very much.
Thank you very much, Dr. Roots, for the great presentation. This tool is truly a great example as it facilitates the interpretation of this long-term data in multiple locations, as well as help us to understand some correlation among these locations and the two main types of data, the water level and salinity. I think it also allows for a quick overview of those observed trends and a very user-friendly interface. So I think it's a great example. And then here comes our challenge, which is having the capacity to implement those metrics district-wide and also facilitate as much as possible the user interaction. So our plans include the development of a story map organized according to the final defined categories of data. We are still working on that, and also providing a quick overview of where the data is available and observed in each location. So associated trends and data analysis that will be produced in each of those locations with the quick access to the user. The goal is to have those main data results analysis, associated charts, and in addition, any data really updated through our recently launched DB Hydro portal, DB Hydro Insights portal. This is a tool that was launched a few months ago. If you didn't have the chance to explore it yet, please go ahead and try. I think we have a better version open for comments. It's very user-friendly, it's very interactive, and we are hoping we can link this tool to our story map to have a very easy interaction and access to the data. Therefore, once we have a final design determined, we will have the capacity to really have the latest data included in those trend results. In parallel to this real-time interactive web-based tracking tool, we are also coordinating to have our major scientific findings published annually as part of one of our existing publications. So far, we have pre-selected the South Florida Environmental Report as the potential publication that could host a new section to allow for a more extensive technical discussion on these metrics. And we are planning to do that in a rotation basis according to major highlights and shifts that is observed on specific metrics each year. We don't expect to see a lot of change in those trends every year to all the metrics. So we are planning on a rotating basis to be publishing those more scientific analysis. So among our next steps, we will be incorporating your comments and continue to advance the district-wide implementation of those metrics, and of course, giving a final set of metrics. We hope this initial selection is relevant, and we are already receiving some suggestions to incorporate additional, for instance, biological metrics as well as metrics related to potentially increasing stormwater volumes and associated flows. We anticipate having continuous scientific analysis that will help us to further establish correlation with climate change as an influencing factor, among other recognized several influencing factors, such as the operational chains, other environmental conditions. We recognize the need to differentiate some metrics that some are more driven really by climate and I would say uncontrollable processes, so such as rainfall, and we have also metrics that are more a consequence or a result of many conditions that can be controlled by the way we operate or manage our system. So I believe the water quality presentation here today included a great example on how this additional analysis might be evolving in trying to determine these influencing factors on more complex observed trends, and also our capacity to tease out this climate change impact as appropriate and as possible. Maybe we will not have the capacity to answer all these questions right away. And I think the ionic composition, again, the water quality presentation proved that the ionic composition seems to be the dominant factor in what we saw as observed specific conductance trend analysis results. But that doesn't mean that we will not maybe find something else in the future with these metrics, with the additional metrics and additional locations that we'll be bringing. So, and we also think it might end up resulting in recommendations on how can we better monitor some of those metrics. And finally, we anticipate that once we have established those robust observations and the associated trends, we can use this information to support the estimate of future projections. We see this effort as really a first step in providing water and climate data in science readily available data to the stakeholders in South Florida, and we count with your continuous engagement and support to this process. So as a reminder to all the participants, please type your questions in the QA box there in the bottom of your Zoom screen. We will begin responding to those questions now, and we will keep it open throughout the Q&A session. So go ahead and send us your questions. And I would like to invite Yvette now to see if we have any questions that were not answered yet, and then if you please can help us read and go through those.
Sure, Dr. Moran. We have one question, actually two now that popped up. There's a question stating, is any evidence that the shifting indication anion ratios impact pH? If so, is there a pH trend?
Ninad, can you help us?
Ninad,
yes. This is, I believe, a question that Fred Sklar asked. Yeah, we did a seasonal Kendall test on pH, and it was a borderline significant, insignificant. There is a increasing trend, but the increasing trend is so low that probably that's why the trend is not significant. But the pH actually was slightly lower in the in the early 70s, and has slightly increased during the more current period. So there is a shift in pH, and we can see that trend, but it's very, very small. We're dealing with a pH scale, which is a log scale, and small changes are very hard to see.
Thank you,
Okay.
Nina.
Okay, great, thank you. And then for all those that are asking if the presentation, a copy of the presentation, it is on our website under the calendar. If you'd like to go there, I can explain a little bit more on how to get there, or we can answer that question online also. And then the next question is from Dorothy Cifuentes. Evaporation is a small component of ET relative to transpiration, spatially and volumetrically within the district boundaries. Could E reflect a different trend than T, depending on land cover, climate patterns, etc.? While the draft metric is more focused on E and PET, could emerging spatial estimates of actual ET be more useful and incorporated to the metrics?
Kevin, can you help us answer this question?
And if it can't be answered in line,
Hi.
you can get back.
Hi, this is Kevin. Can you hear?
Okay, Kevin. Yes, we can hear you.
Okay. The first thing is in the presentation, we have both evaporation and ET. From some documentation, they say evaporation is a small component. This is, if you look at in the whole world, but for South Florida, we are in a wet situation. We have a lot of wetlands and we have a lot of the open water bodies. So probably in South Florida, evaporation is a big component of the total ET. And there is a well-known the ET is called the simple method, which was developed in the district. That formula was totally rely on the data collected in the SPA, is in the man-made wetland, and is widely used in South Florida. So for South Florida, I would say evaporation at least is equivalent to the transpiration. If you look at the USGS data, it's the potential ET. Actually, for this parameter, it includes the evaporation and transpiration. And I hope this answers the question. If any further questions, I would answer later.
Good, yes. And if we need any clarification, please type your question again. We'll be happy to answer additional questions here.
Okay, and then we have additional questions from Dr. Pretzkelar. Question for Carlos. In your summary, you mentioned a white zone. Can you explain what this is and if it responds to sea level rise?
Thank you very much for the question. Yeah, the white zone. We cannot see the map, right, of the presentation.
I can go back just a second.
Just the map.
Okay.
Thank you. No, the map. Next slide. No, down. Now one up. Is the map showing all the study areas? Next up. This one. So this is the map showing all the different sites where we've been monitoring elevation change. And the question is, what is the white zone? The white zone is pretty much all this pinky, the color, more or less pink color in this map. And it's more or less to show where the white zone is. And the white zone is described as a zone where has been a shift in the species composition for the last 60 years, more or less. So the white zone in 60 years ago in the 1940s, it was an area dominated for graminoids plants, and it was plants that were more associated to fresh water. Today, the white zone is a different species composition dominated by red scrub mangroves, shown on those two pictures on the left, and is the area where we, for this particular study measuring soil elevation, is where we've been observing a loss in elevation on those sites that are located within the white zone. So if this trend continues, the trend of losing elevation within the white zone, we might expect to see that the white zone will become an open water over the next 20, 30 years, more or less. I don't know if I answer your question, Fred.
Okay, thank you. The next question is from Alan Drew. Does the district estimate carbon storage across the system or in any specific areas, e.g. the Everglades agricultural area, and our greenhouse gas impacts, e.g. from land use changes or changes in pumping, being assessed or considered in this work?
I'll take that question, Yvette, and thank you very much, Galen. This is a great question. And this is part of some of our next steps, I would say. I will ask, we have also our bureau chiefs here in this call, and if they want to add anything to what I'm going to answer, please feel free to add. But so I was not exposed to any specific long-term data series that we have been tracking carbon storage in any specific area. And also with regards to the greenhouse emissions from both land uses and especially from pumping, we recognize this as an important factor. We are not yet tracking. This is one of the reasons when we talk and when we receive a comment and a suggestion on monitoring the excessive volumes of stormwater, the increasing stormwater volumes and the increasing discharge, that's exactly related to the pumping. In 2020, we also had, compared to the previous years, we also had a very an increasing number of hours that our pumps and our system was operated, given this amount of rainfall that was way above the average. So that's definitely something that we want to track. We focus the initial part of the work on really long-term data that we have on trying to establish those trends. But a lot of guidance, I believe a lot of guidance will also help us on understanding key metrics that we need to start monitoring now and maybe establishing those trends into the future. So I'm not sure if anybody would like to add anything to my answer, but I hope that also helps to answer your question.
Okay, I have no additional Q&As in the queue. If you'd like to move. Oh, yes, a couple just popped in. Okay, so this is, and the next question is for Fatih Purdue. Are you planning to investigate the effort of long-term climate cycles such as AMO and PDO on long-term trends and possibly consider them in the future rainfall and water level estimates?
Yes, this is also part of our analysis, and I'm not sure if Ali would like to provide additional information. But yes, this is definitely something that we are attentive.
Did you want to add to that? Okay,
this is Corinne Smith. I would just add that on the water level estimates, it's hard to do that with the climate because so much of our system is managed and it's not, solely based on climate. So getting water level estimates will be more difficult because we have a very managed system, at least on the East Coast. That's all.
Something that I would like to add to with regards to AMO and PTO and even any other multi-decadal phenomenon, we understand that this is very important when we try to establish our trends because, and rainfall is the best example here, because if we look at some periods of our history and if we isolate the trend to certain periods of time, we will see very different trends occurring throughout the historic observations. So just to give you a quick example, if you start your time series in the 70s, 80s, and 90s, and you look at the entire South Florida region, what is the trend? You're going to see complete opposite trends in rainfall, increasing and decreasing, depending on how you start your analysis. And this is really truly a result of those oscillations that occur that are also being tracked and also considered as part of those analyses. So our goal, what we decided so far is to use the entire period of data that we have in those trend analysis and observe the trend in the very long term. We believe this is the most, I would say the most appropriate way to display this data and to display the trend. But of course, there are a series of additional considerations that we will be evaluating as we go and we refine those analysis. But thank you for this question.
Thank you, Dr. Moran. The next question is from Michael Zanurski, and if I pronounce your name wrong, I apologize. But his question is, many interesting and useful metrics presented today. In beginning of the presentation, a grid-based analysis of the ETA rainfall against frequency was shown. This would be a great tool to make available for other storms. Often city and drainage districts or even general public try to access these systems response to rain events by quantifying the local storm intensity. So it's not actually a question.
Yeah. Thank you, Mike, for this question. This is a great question. Actually, this is a new tool that we created recently as part of the FPLOS program here, exactly to describe what you understand as important information. So basically what we did is we used the next red grid and we compare so basically, we brought the NOAA Atlas 14 data to the next red grid. So what we can see is how the recent events and the observations that we saw compare to the return frequencies, grid by grid, as determined by the NOAA Atlas 14 equations, the return frequencies established by the NOAA Atlas 14. So I agree with you, it's a good visual tool. We have, I believe we have results for the May 24 event. We have for Tropical Storm Isaias and Tropical Storm Eta this year. And we are obviously able to provide maybe some support to have this information available to you at every major event that we have been tracking.
Okay, and this concludes the Q&A. I have no additional Q&As on the queue, but we do have several hands raised if you'd like to go to public comment.
Sure. Go ahead, Yvette, and we can transition to public comments.
Okay, so public commenter Diane Goldberg. Goldberg, if you can please unmute. Thank you.
Yes, good morning. Thank you for this program. This is really insightful. So basically what I'm getting from this is that we are seeing an increase in sea rise and even groundwater levels are increasing. We are finding damages or increased damages to ecosystems, and there has been a hydrology change, and saltwater intrusion is happening, as well as water quality decreasing. Are you going to be having studies now or meetings to decide what is going to be done to help these situations, what the public can do, as well as what scientists and governments think we should be doing?
panel members? Dr. Moran, can you hear?
Yes, just to
Okay.
clarify that I can answer this question and I'll be more than happy to answer, but the goal of the public session was not to go through question and answer, just the comments. So if you have additional questions, just please type in the Q&A session. And yes, Mrs. Goldberg, thank you very much for the question. This is why we have a resilience office now at the district, and not only now, but the district has been doing a lot of work in the past to address those issues that we are observing and helping just to share this information with the public at this time. So we have several programs, and I mentioned the flood protection level of service a few seconds ago. This is one of our major programs that we do in order to address increasing flooding risks that are a result of those observed trends and climate impacts. And not only that, but of course, change in development and other things that are contributing to the increasing floods that we observe. We also have a very robust monitoring program for the saltwater intrusion. We publish a saltwater interface map every 5 years, and we monitor this throughout those years. And there are a series of additional initiatives that the district is pursuing in order to address and prioritize investments to harden our system and protect our mission, the delivery of our mission to the South Florida communities. So thank you very much for the question.
Thank you. I have two Q&As that just popped up. Dr. Moran, would you like to go back to the Q&A?
Sure, we can go back.
Okay, so it's from Bernal Civil. Are there any correlations between SWM performances during major storm events and LMI areas?
Bernal, I am sorry, but I'm not sure what LMI areas is, and I'm not sure if Karine can help us answer this question.
I was just wondering what LMI stands for also.
I thought it was just me, and I was feeling so bad.
Okay. They write here low, moderate income areas.
Oh, sorry. Okay, thank you.
Carol Schumann answered.
So I don't believe we have any specific study yet in regards to saltwater monitoring and performances during those major storms in the lower income areas. I believe some of the locations where we see a movement of the saltwater front might be coincident to those lower income areas, and we have to account for those a little bit more specifically, but we have not advanced in a specific study focusing on these areas yet. Karine, are you aware of any additional effort from the district?
Not from the district. I would say the counties have been doing it, like Miami-Dade. I've read some things, and I assume that you would probably know Broward better than I would. But and obviously, you know, this is not just the East Coast. The Lower West Coast is also, you know, part of this too. But I'm not aware of anything that we've done.
Thank you, Karine. Yes. So we'll keep, thank you very much for this question, Mr. Sibo, and we will be considering your suggestion as well and incorporating maybe a special look at those lower income areas and see if there is any specific condition that is more, somehow more evident in those areas. Thank you.
Thank you. And the next question, Q&A, is from Diane Goldberg. Due to all the increase in damage caused, what do you think the public and government should do to help?
Thank you, Mrs. Goldberg. And I think I didn't answer this part of your question originally to what the people can do to help. And I appreciate you typing it again. So I think the first thing is to get informed. That's one piece of what we are trying to do here with this data. Data is what will help people to understand the problems and guide us through the solutions. So be engaged and trying to be informed and understanding what's happening is the first step. We have also, I think one key aspect is that we have and we strive to have good public participation in all our planning efforts. And this is a challenge because it's hard to really find the time and have all the key players that should be really engaged in all those planning efforts and through the development of those projects that we do. So I think one important thing that people can do is really find ways and prioritize some of those projects that are key and really participate actively, bringing your opinion and how you are really evaluating the solutions that are being proposed throughout those efforts. And of course, be engaged with the local governments, with the county governments and all those organizations that are also developing and implementing those solutions. I think resiliency plans are becoming more and more common in all those levels of government. There is a lot going on now and a lot going on in the future. And I think we need to be aware and find the time in our agendas to really be engaged and participate in those processes.
Okay, the Q&A section is, one more, hold on, Courtney Stevenson. What are the most important things water quality companies can do with regard to saltwater intrusion?
Water utilities. Do you want to answer, Karen, or do you want me to answer?
Sure. I was in regulation for most of my career. Really they have to do monitoring and keep a track of how the front is moving, at what rate it's moving, and be ready to, have alternate sources of water. And that of course requires funding because any alternate is going to be more expensive. But we're just going to get to that point where, because the real thing is that, it's the simple answer is, okay, just go inland. But inland is environmental, and the environment needs the water too, and it's protected. So the options become limited. And so then you just have to go deeper and just treat the the poorer quality water, and it's more expensive. But really they're not going to be able to stop saltwater and, the sea level rise. So it's just a matter of monitoring the rate and then deciding how to, another option, which will eventually probably happen, is just using, even though the front passes them, continuing to use the wells, but switching to a different treatment method because they're now brackish water instead of fresh water. But we haven't quite gotten there in our rules. So that will be coming, I'm sure. Yeah, and then the other big thing is we also, the new thing is potable reuse. So reusing water is huge, because the more we can reuse, the less we have to use the first time around. So water conservation, of course, too, same thing, reduces how much we actually have to pump. We can serve more people if we don't use as much.
Yes, you read my mind. I was going to say that we have all those alternative water supply options that we are investing to, especially conservation too, which will help us to really reduce as possible the per capita consumption, and would help us to maintain our aquifers in a level that would help to prevent saltwater intrusion. So the less we pump, the more we can fight with the saltwater intrusion. And something that Broward County Water and Wastewater Department is doing is they have a special permit that is impoundment and diversion permit that allows them to move water in the system, because they also manage the stormwater system. So that's an advantage that they have. They can manage a little bit the canals and maintain certain levels that would help them to avoid saltwater intrusion. So they recharge the aquifers a little bit more efficiently. That would really protect their well fields. This is, I think, a great example that is successful in managing saltwater intrusion in our region. Not all the utilities have this capacity because somehow not all of them can operate this canal system in a way that would allow them to maintain higher stages close to the well field locations. So, but yes, investing in alternative water supply sources and conservation are also key aspects that we need to start thinking before we move to more expensive solutions and really have to remove salt of the water, which is going to make the cost of water in South Florida way more expensive.
Okay. So we can now go, I have no queues or questions in the queue. The public comment is for Nell Sybil. Mr. Sybil, if you can please unmute. For Nell Sybil, if you can please unmute. *6 if you're using a phone. Give him a few minutes for him to unmute, or for the person to unmute. For Nell Sybil, if you can please *6 to unmute.
Let's move to the next one, and then we can go back to Mr. Sybil next, Yvette. Thank you.
Yes, I do not have any additional hands raised.
Okay. Any additional comments? We welcome comments in general from the participants. And if you have any additional question, feel free to send us to, I think Yvette provided some instructions on how to type later to send us questions.
Okay, at this time, I do not have any Q&As to be answered for additional hands raised besides for Nell Sybil, that unfortunately we cannot hear you.
Okay, so if no more comments and no more raises, no more hand raises, I think we are ready to adjourn.
Thank you all for participating. As Dr. Moran stated, this meeting is adjourned. Oh, I'm sorry.
Sorry.
Yes, there's
It's
one that
fine.
just popped up. Okay, sorry. Okay, so we'll go back to the questions. So Mr. Lee Worth Jr., is the district also looking at the effect of rising of waters on the confined aquifers along the West Coast that outcrop on the Gulf of Mexico?
Yes, we also have stations. So some of our control stations that we are also have the capacity to measure elevated tidal elevations. Sorry, in this West Coast. Our saltwater monitoring mapping effort also includes the different layers, aquifers in the West Coast, and there is a specific space in our website that provides all the access to all this information and all the aquifers along the West Coast I'm not sure if Karine or any other participants here, panelists here today would have additional information to provide to Mr. Wurst.
I haven't looked at the effects over there, but I know we just finished the modeling over there of the superficial and the intermediate. So then some of those are confined aquifers. And so we've been carefully looking at the data for the last, that covers like the last 30 years, but not in the context of resiliency. So, but we do have all the data and I can get with them.
Perfect. Yes,
Thanks
thank
for
you
the
for also talking about the modeling efforts that would help us to understand all those factors and those impacts. We can give a few more seconds, and if not,
If you'd like to speak, please raise your hand.
yeah, we welcome
give you-
any comments
yes.
in general. Any additional questions? We can be here. We have the time.
Okay, I don't see any additional questions and no questions and answers on the queue.
Okay, so we are ready to adjourn.
We will adjourn. Okay, great. Thank you everybody for attending, everyone for attending in this meeting. As Dr. Carolina Moran stated, it is adjourned.